Drop a few ice cubes into a glass of water, and they immediately bob to the surface. It happens every time, but according to the standard rules of physics, those solid cubes should sink straight to the bottom. Cooling a substance almost always causes it to contract. As the temperature drops, the volume decreases and the overall density goes up. Think of the atoms in a liquid like kids in a fenced playground. They are free to run around, bumping into each other and shifting positions, but they stay within a contained space. When that material freezes into a solid, those same kids are called inside and locked tightly into assigned seats in a classroom. The structure becomes rigid, the atoms pack closely together, and the material becomes much denser than the liquid it used to be. Because water refuses to follow this rule of tight atomic packing, ice floats. It is a highly visible physical anomaly sitting right in your glass. Archimedes' principle states an immersed object experiences upward buoyancy equal to the displaced fluid. A dense iron chunk weighs more than this fluid, pulling it downward. But a less dense object experiences stronger upward pressure, pushing it up to rest on the surface. Liquid water sits at nearly 1 gram per cubic centimeter, while solid ice is exactly 0.917. As a result, exactly 90% of any floating iceberg remains securely submerged beneath the waves. Why does water expand and lose density when it freezes, instead of packing tightly together? Water molecules act like tiny magnets with positive and negative ends, creating sticky electromagnetic attractions. As temperature drops, these magnetic poles force the molecules to lock into a rigid hexagonal pattern instead of a dense pile. That six-sided structure acts like a microscopic scaffold, creating empty, porous space between molecules and physically forcing the ice to expand as it freezes. This geometric shape overrides standard compression. Ice takes up more physical space, and therefore it floats. This expanded, porous structure creates a bizarre situation when you expose solid ice to extreme physical pressure. For most materials, squeezing a substance hard enough forces it into its denser phase. If you compress a gas, it turns into a liquid. If you compress a liquid, it becomes a solid. This chart maps the phase boundaries for water. Because liquid water is denser, adding pressure forces solid ice to cross the boundary. You actively lower the melting point, crushing the ice into a liquid without applying any heat. Water is incredibly rare in this regard. Squeezing the solid form actually shrinks its molar volume, the total amount of three-dimensional space occupied by 1 mole of the substance, and turns it into water. You have likely experienced this exact pressure paradox anytime you've gone skating across a frozen surface. When you step onto the ice, your entire body weight gets concentrated down onto the tiny surface area of your shoe sole, or the incredibly narrow edge of a skate blade. That immense pressure instantly assaults the rigid hexagonal ice crystals beneath your foot. The weight forces those crystals to compress, collapse, and melt. This creates an ultra-thin layer of liquid water between your foot and the solid ice underneath. That microscopic layer of water acts as a perfect temporary lubricant, causing your foot to slide. The exact same molecular quirk that forces a massive iceberg to the surface of the ocean is why you can glide across a winter rink.